So we were talking about non-coherent detection. Uh, the rule that can be applied at the receiver side to detect either the signal sent was the vector xa or xb. The distribution of the received vector y is given by complex normal distribution with mean 0 and variance of the transmitted vector. Similarly, if the transmitted signal is xp, the distribution of the received vector y is given by complex normal distribution with mean 0 and uh, variance matrix given as such. There is a difference between both of these variance matrices, which can be directly seen from the symbol vector transmitted A and the symbol vector transmitted B. So the log likelihood ratio is the best estimate that can be used, or is the sufficient statistics that can be used to differentiate either XA or XB was transmitted from the PDFs of the transmitted signal XA and XB. If you see in detail, this equation basically represents a comparison of distribution of XA and XB when the distribution is measured at vector y. Solving this equation and putting the respective PDFs, we get this equation. So from this equation we see that this turns out to be a very interesting decision problem, which is called energy detector. So from the energy detector, what we get is that the estimated received signal X is equal to XA if we compare the energies of the received signal at timestamp 0 and timestamp 1. So if y0 is greater than y1, we estimate it to be XA. If y0 is less than absolute value of y1, then the transmitted signal is given as XB. If you see this diagram here, this basically gives you the very clear idea that the projection of the received signal on two axes. One axis is the time symbol transmitted at m is equal to 0, and the other axis is at m is equal to 1. So XA is on m is equal to 0 scale, and XB is equal to m is equal to 1, which is the y-axis. It's a two-dimensional plane. So the y received vector would be a point on this two-dimensional plane. If you project the values of y on the horizontal axis, that would give you y0, and if you project the point on the vertical axis, that would be y1. So the lengths of these y1 and y0 can clearly give you an idea of what symbol was transmitted. So now we will calculate the probability of error. So if we are given x is equal to xa, y would be given as complex normal distribution 0 and this variance matrix. So what is the distribution of y square? The distribution of y square is given by an exponential distribution with argument 1 over a square plus sigma square, and the distribution of absolute value of y1 square, which is at the second time instant, is given by exponential of sigma square to the power minus 1, or exponential with argument 1 over sigma square. Now we should keep in mind that y0 square and y1 square are independent. Hence the probability of error is given by the probability of this value is greater than the probability of this value. So when you calculate and put the values of these probabilities, which will be shown in detail in the notes is given by 1 over 2 plus a square plus sigma square, that is equal to 1 over 2 into 1 plus SNR. Now we compare the average error probability of PPSK signaling in AWGN and Rayleigh faded channel. In AWGN, the error probability decays faster than e to the power minus SNR as given by this equation. Okay, because this is the probability of error of AWGN, which can be approximated by 1 over under root 2 SNR under root 2 pi e to the power minus SNR. This value is approximated at higher SNR. So the Rayleigh fading case, the error probability decays as 1 over SNR. So the coherent detection and non-coherent detection gives specific values at higher SNRs. The probability of error at higher SNR for coherent detection turns out to be 1 over 4 SNR. Similarly, for non-coherent detection, the probability of error turns out to be 1 over 2 SNR at higher SNRs. This graph gives you a comparison of probability of error for variable SNR for different types of channels. This graph, the dotted line, is basically the non-coherent orthogonal signaling. The small dotted curve gives you coherent BPSK for signaling, and the bold graph is for BPSK signaling over AWGN channel. So if you compare the coherent and the non-coherent case, there is a difference of 3 dB, and comparing this with the AWGN case, there is a difference of 15 dB. Now you can also use QPSK, which has more degrees of freedom and less energy used compared to PAM. PPSK only makes use of real dimension, that is the I channel, okay, or in the in-phase channel. This rate can be increased if we use additional bit on the imaginary dimension, which is called the Q channel. So the symbols, the various symbols that can be transmitted through QPSK, they are not 2 anymore, they are 4, given by these 4 combinations, and then shown on the constellation diagram of QPSK with real and imaginary axis. We have 4 points. These 4 points correspond to these points given here. This point is B into 1 plus J. This point is minus B minus 1 minus J. This is B minus 1 plus J, B minus 1 minus J. The SNR turns out to be 2 times B square over sigma square, which is the double of BPSK. Now the bit error probability or probability of error of a bit is simply a product of 2 BPSKs, because if we only take one imaginary axis or a real axis at a time, it is basically a BPSK. So combining these 2 BPSKs is simply the product of 2 BPSKs. So analysis is the same. Simply replace SNR by SNR over 2. In the Rayleigh fading case, we get 1 over 2 SNR at high SNR, and for AWGN we get Q into under root 2 SNR. So the degrees of freedom in QPSK, they are more compared to the degrees of freedom if we equivalently use 4 PAM. The symbol error probability is approximately equal to 2 times Q into 2B square over sigma square, and for 4 PAM the symbol error probability is given by 3 over 2 Q, an argument of square root of 2B square over sigma square. A complex scalar channel has 2 degrees of freedom. Now BPSK only uses 1, but QPSK uses 2. That is, QPSK rate is doubled. Even QPSK is more energy efficient than 4 PAM, approximately 2 times 2.5 times more energy efficient than 4 pm. QPSK average transmit energy is given by 2V square, and for 4 pm average transmit energy is equal to 5V square. Now we talk about the typical error event. What is the deep fade? In Rayleigh fading channel, regardless of constellation size and detection method, either we use coherent or non-coherent communication, the probability of error is proportional to 1 over SNR. Now if we calculate for BPSK, the probability of error for given h is given by q into under root 2 h square SNR. Now if h square is a lot greater than 1 over SNR, the conditional probability is very small. If h square is smaller than SNR, 1 over SNR, the conditional probability is very large. So the total probability of error is given by this equation, in which this part in highlighted in blue is the probability of deep fade. So this whole probability is basically dependent upon this probability, which is equal to 1 minus e to the power s 1 over SNR, which is approximately at higher SNR is equal to 1 over SNR.